like an order of like.
Okay, PS1 is out and due Thursday and Friday. Any questions or problems about that or anything? Yes?
I could be wrong, but I thought last time I checked that they were all due Thursday. Like all
It's Thursday.
I think the first three are due Thursday and the last two are due Friday.
Yep.
Typically, the CAS problem will always be due on Friday, and sometimes there are problems that follow on from the CAS problem like this week, so that's the fifth one. It's also due Friday. Anything else? Yeah?
Are you going to go over how to evaluate like the n squared plus 1 of algorithms, or is that something we're going to focus on our own time?
Okay, I'm not sure what you're asking. The n squared
like,
plus 1.
In the third set of problems, we're looking at a set of array, and we're trying to work out what time it will be in based on the size of the array. Is that something we're going to go over in class, or is that something we need to focus on outside of
Okay.
class?
So yeah, he's asking about problem 1-3, and yeah, I could work through an example of that.
Please.
Okay. Let me see if there are any other questions first. Okay, a couple things I want to point out. So right here on the home page in Canvas, there's a link to the videos here. So you'll find the posted videos. That just takes you to YouTube, to a YouTube playlist where I put the videos after class. And we now have, if you click on help here, we've got the staff help hours up. So as you can see, we got hours all 5 days here, quite a few on Wednesday and Thursday, fewer on the other days. Some of those times have 2 TAs at the same time. You don't see that in the schedule. And notice that where they are depends on what day it is. So Monday, Tuesday, and Wednesday they're in 3105 MEB, and the other 2 days they're in 3159. But they're pretty close to each other and close to the front office. Okay, so 1-3 I happen to have here because I knew someone would ask. They sort of all follow this form. I tell you an initial arrangement of numbers. And so this says, suppose you have an array that contains n plus 1 integers. And it starts at 0, and the rest of the numbers are arranged into descending order. And you're supposed to count how many comparisons will be performed by insertion sort in that particular situation. And it's one thing to solve it for a particular n, in this case 8, but I want you to solve it for the general case. Okay? All the examples I give are using n equals 8. So the first thing to understand, you have to know, is how insertion sort works. So let's make sure we all understand that. So we here have our array. I'm going to cut the size down to 8, although this 8's different than that 8. The problem talks about 0 through n, which means there's n plus 1 numbers. This is 0 through 7, so there's exactly n numbers, but you can get the idea. So if we take the order and permute it, let's try to figure out how many comparisons insertion sort will have to do to sort this array. So what's the first comparison insertion sort does?
between the first and the second element.
Right, it'll compare these two elements. So it doesn't bother with this first element because, that was weird. So it goes, what it's going to try to do now is push this guy here as far to the left as it can until it gets as far but no further. So if I step, you'll see it compares them. And this guy is bigger than that guy, so there's no swapping needed to be done. So that's one comparison. Okay? Now what's going to happen is it's going to try to push this one as far to the left as it can. That's not right.
Shouldn't it compare with the second number?
Yeah, it should be compared. Let me try again. Okay, let's see what we get. So we compare those two. Oh. Yeah, let's do insertion sort. Okay. Okay, so it'll compare those two, and since the one on the right's smaller than the one on the left, it will swap them. Okay, now it's got these two in the right order. Now it's going to look at this one and try to push it in the right spot, so it'll compare this one to the one next to it. So that's another comparison, and no swapping is necessary. So then it's going to try to push this into its place, so it does a comparison, and a comparison. It's kind of weird the way it's being animated. But you get the idea. So now it's going to do that comparison, no swap necessary. It'll do that comparison. It's going to do a series of comparisons as it moves the thing to the right spot. So that's how insertion sort works. We do a series of comparisons as the thing trickles down. So this guy is now going to do a comparison all the way down the line and get in the right spot. And then there'll be a single comparison there, no further action, and the thing is done, and it did 18 comparisons. So the problem consists of telling you a specific way that the numbers are arranged initially, and you have to say how many comparisons are done. So let's just work through an example. So I need to pick an initial order, hopefully one that's not in the assignment. So let's say it's done like this: 0, 1, 3, 5, 7. 2, 4, 6, 8. Is that one in the problem? Anybody want to tell me?
I don't think so.
Yeah.
I think the evens and odds swapped.
Okay. So here, the description would be that you've got 0. 0 is always first in all these problems. Then we're going to have all the odd numbers in ascending order, and they're going to have all the even numbers in ascending order. And the question is how long it will take, how many comparisons will be done by insertion sort. Now, I think the best way to attack this problem is to, well, one way is to, you can start with something smaller. You could start with 0, 1, 3, 2, 4, which follows the same pattern for a different n, and do some counting just to get used to what the pattern is going to be. The next thing you want to do is essentially treat the odd numbers differently from the even numbers. So let's try to figure out, even though I'm writing the numbers 0 through 8 in some order here, and so our n is equal to 8, let's solve the problem for this, let's work on the problem for this example, but as we build up momentum on it, we'll be able to sort of see what the general answer would be. So let's, how many comparisons are going to be done just dealing with these odd numbers right here?
1.
Well, let's see. It's going to compare the 1 to the 0, right? And no swap. It's going to compare the 3 to the 0. I'm sorry, the 3 to the 1. No swap, but one comparison. It'll compare the 5 to the 3. That's another comparison. And the 7 to the 5. That's another comparison. So in this case, it did 4 comparisons. 1 for each odd number. So if you generalize this to n equals 8, how many comparisons would it do? Right, n over 2. Right, you see where that came from? They're always going to be n over 2 odd numbers. Each one, we do one comparison for it. So in this particular case, for n equals 8, we're doing 4 comparisons. And in the general case, it'll be n over 2 comparisons. Right? And we didn't have to rearrange this as we went. But if rearrangements were required, we would need to be showing how the array changed in order to do an accurate count. So let me copy this down here so that we've got some room to work. No. Okay, remember that, n over 2. So it was 0, 1, 3, 5, 7, 2, 4, 6, 8. Now let's deal with the even numbers. How many comparisons are going to be required here for the 2? So it'll compare it to the 7, and then the 5, and then the 3, and then the 1, and then the 2 will end up right there. So how many comparisons was that? 4. Okay, so it did 4 comparisons. Now, what about the 4? So it'll compare it to the 7, the 5, the 3, and since 4 is bigger than 3, it'll stop there. It'll stick the 4 right here. And that was 3 comparisons. And what about this 6 right here? Right, it'll go 6 to the 7 to the 5, and the 6 will end up right there. And that was 2 comparisons. And then for this 8, it'll compare it to the 7 and stop right away. So that's 1 comparison. So in this case, it's 4 plus 3 plus 2 plus 1. And it's not hard in this case to see how that's going to generalize as well. What would it look like if n were equal to 10?
5 plus 4 plus
Yeah, it'd be 5 plus 4 plus 3 plus 2 plus 1. So what about for n for the general case, where they're for n, where the highest number is n? Right. So it's n over 2. This number right here is going to be half of n. You know, for 10 it was 5, for 8 it was 4. So that it might help to play around with a couple different lengths, but you quickly see that you get this sum, and you sum from n plus 2 down through the integers to 1. And on the previous slide, we got our answer as being n over 2. So here's something you don't want to do. I tell people to consider. Often it helps, not always, but usually it helps to split to the even and the odds and sort of find the general case. Look for a pattern, find the general case. What you don't want to do is come up with this 4 plus 3 plus 2 plus 1 and then add it up and say, okay, that's equal to 10. And then do it again for n equals 10 and come up with a different number like 15 and try to look for a pattern there. You want to look for the patterns in the summations. If you sum them, you sort of lost the information you need. It's easier to see if in one case you get 4 plus 3 plus 2 plus 1, and in the second case you get 5 plus 4 plus 3 plus 2 plus 1. That pattern is obvious. If instead you've got to say, okay, in one case I got 10, the other case I got 15, what the heck does that mean? Okay, so what is it? Let me pause now and see if there are any questions. Okay, so essentially you're always looking for, you'll generally be looking for summation like that. And this summation here was really 1 plus 1 plus 1 plus 1 n over 2 times, but that's easy enough to turn to n over 2. What's it take to bring the solution home now? Add them up. Well, what's this thing equal to? Okay, what's the sum of the first k integers? Yeah?
K times k plus 1 over 2.
Right. The sum of the first k integers is k times k plus 1 over 2. It's just one of those things that's really handy to know. So the sum of the integers from 1 to 100 is 100 times 101 over 2, or 5,050. The sum of this sum right here is going to be what then? If k is n over 2. It's going to be n over 2 times n over 2 plus 1 over 2. Okay, we're just plugging in n over 2 for k. And you might ask, what if n is odd? But it's not odd. The problem says it's always even. And then that's the comparisons for the even part, and then we need to add another n over 2. Now, if you enter your answer like that, I will be displeased because I can't possibly, the autograder that's used is looking for certain answers. And it doesn't do math simplification, so I can't tell it, count correct anything that looks like this or is equal to this thing. So I've asked you in the instructions to simplify things as much as you can. We do make a manual pass over it at the end to pick up any things that were counted wrong by mistake. So you don't have to be too paranoid about that. But don't be sloppy. Okay? Simplify it. So what will be the simplification of this?
Squared over 4 plus 1 over 2 over 2 is
All right.
8 plus 1 over 4.
Multiply through, we get n over 4 plus n over 2.
Should be n squared over 4.
Thank you. N squared over 4 plus, n over 2, okay, plus n over 2. So that's n squared over 8 plus n over 4 plus n over 2, which is 1/8 n squared plus 3/4 n. That's sort of the form I want you to do it in. Now, if you're like me, you might wonder, did I make a mistake in simplifying it? So what's a good sanity check to do before you hand it in? You just plug in some ends you know the answer to. So for n equals 8, this would say 1/8 of 64, so that's 8 plus 6, so it would predict 14. And I don't know, is that what we got? We got 4 plus 10, 14, yeah. So try it for for a few small ends to make sure you didn't make a silly mistake somewhere. And the way I would have you enter it would actually be 1/8 n squared plus 3/4 n. We're going to assume these parentheses are implied, so don't. Oh well, I just messed it up. But I wonder if Control Z works. Yeah. Yeah.
If we submit multiple times on Canvas, does it take our best score?
Okay. You can. For Caddis we take your best score. For Canvas we take your most recent. And let me warn you about something from Canvas if you don't know this. If you open up a quiz, a lot of people take a quiz, and then they want to go back and see how they think they made a mistake, so they want to look back at what answer they gave. Once you open it back up, you're taking the quiz again. And if you just leave it blank and abandon it, when the deadline passes, it will submit as a blank quiz, and it'll grade as a 0. And then you will contact me, and I will fix the problem. But every time that happens, I get a little annoyed, but mostly at Canvas. I try to screen for that, but just be aware that that can happen. If you see a 0 pop up that you didn't expect, let me know. Any other questions? Okay, so we're talking about asymptotic complexity notation, big O notation, and where that comes from. It's one thing to understand what it means to say that insertion sort is O of n squared, but we're able to derive things like that for iterative algorithms is very often by doing counting like this. You have to do very careful counting in the general case, figure out in the worst case how many comparisons will be required, and that gives you the bound you need. But to do it, you got to be able to count. Perhaps not this exactly. You really just need to be able to count exactly enough that you know that the higher order term is an n squared term. But that's the game when you're doing complexity analysis on iterative algorithms, is counting. Now, why do we count comparisons instead of something else like swaps or number of times that the index variable is incremented in the algorithm? Yes?
Comparisons are slower.
He said comparisons are slower. That's I'm not sure that's the case, but that's not the reason either. Yeah.
Are they proportional to the other operations? So like they only differ by a constant?
He said, are they proportional to the other operations? That's getting at it. It's basically the most common operation. You do at least one comparison for every swap. Typically, you do a bunch of comparisons, and then I'm thinking of selection sort again. You end up doing a few more comparisons than you do swaps. So we want to we count the most frequent operation. It dominates. I won't say dominate as a technical meaning in a minute. So it puts a bound on all the other operations for when you're talking about sorting or searching. Any other questions? No, in fact, that was my question. Okay. Now, last time we were sort of toward the end of class. I thought we needed to be at a spot for the assignment, and I was wrong, because I was sort of hustling through. I'm going to back up a little bit, and as a way of, we can all get back up to speed, but also because I went through things a little bit fast. So this is essentially the point I made last time. There are all these forms of notation to talk about complexity. You got a question?
Yeah, just about the previous thing. So the comparison complexity is always roughly proportional to the time complexity. They're like
The what? What was the first complexity?
comparison complexity.
Well, for comparison complexity, when you're talking about sorting algorithms,
Yeah.
comparison-based sorting algorithms, yeah, you count comparisons. You're talking about binary search or operations on binary search trees, yeah, comparisons you count.
But if you were to do it like a time analysis on the same algorithm, it would be like the complexity would be roughly
Yeah.
similar. Yeah.
Right. So for those algorithms, if it's n squared, order of n squared comparisons, it's going to be order of n squared time. Yep. So we have all this notation. There's the one that everyone's most familiar with, which is big O right here. But there are these others like big omega and little o and theta. And the thing to realize is the game we're playing is we're only concerned with the rate of growth in the long run for functions. So we're not interested in what happens to functions when they're small. We're interested in talking about them when they're big, where n is big, if n is the variable that's varying. And we're talking about the rate of growth, in other words, the doubling behavior. And just like you like to compare integers with less than and less than or equal and greater than, equal, or greater than, you can compare rates of growth the same way. So when I say that f is O of g, that means that g's rate of growth is at least as big as f's rate of growth. G's rate of growth bounds, is or put it in the terms of the slide, f's rate of growth is less than or equal to g's rate of growth. If you know what big O is, you know what big theta is. So if I say that f is big theta of g, what's a way of putting that in terms of big O? Okay, so if f is big theta of g, how do you turn it around? Yeah?
You can also say that it's big O of G.
Well, we can say that g is big O of f. You swap them. So if g's rate of growth bounds f's from above, then f's rate of growth is going to bound g's from below. Okay? So there are two ways of saying the same thing. Just like, if 2 is less than 4, or if 2 is less than or equal to 3, then 3 is going to be greater than or equal to 2. Right? You can turn those around. Now, what if I tell you that 3 is less than or equal to 5? Oh, I'm sorry. N is less than or equal to k, and k is A less than or equal to B and B greater than or equal to A. What do you know? They're equal. So theta, which is in the middle here, is when the two rates of growth are the same. So if f and g grow at the same rate, then they're theta of each other. They're also big O of each other and big omega of each other. So that's those three in the middle are the ones we'll use the most, and if you know big O, you know the rest. Okay? Then we got the weirder little ones, the little o and the little omega, which we won't see much of. And that just says if f is O of little o of g, that means that we're not saying that the rate of growth of g is at least as big as the rate of growth of f. We're saying that the rate of growth of g is bigger than that of f. There's no equality of rate of growth allowed here. It has to actually grow faster. And little omega just turns it around backwards to give a lower bound. Yeah?
So just as like a practical case, I know when we were going over like determining the big O notation of certain algorithms, and you would say like, you know, it's linear plus a little bit. Would that be a case where you would want to use like little o or little omega to indicate that it's, you know, a little bit greater than linear?
Okay, so let's see what we could do with that notation. So we were talking specifically about, let's say merge sort. Merge sort is actually theta of n log n, unless you optimize it in certain ways. So, but vanilla merge sort is going to be theta of n log n, and I'm making sure I'm saying the correct statement. So what would its doubling behavior be? If you double the size of the input, what happens to the running time? It'll double plus a little more because of that log n term. Okay? So on the other hand, something like, say, a linear search for an element in an array of length n is theta of n. And there the doubling behavior is if you double the size of the input, you double the running time exactly. Now let's call this f of n, and this is g of n. I don't mean to call that f of n and g of n, but let's say that f of n is this and g of n is that. Okay, how could you characterize the difference? How could you use little o correctly to talk about the difference between f and g here? Yeah.
Could you have g is little o of f?
Okay, could you say this? G of n is little o of f of n. Okay, is that true? Is the rate of growth of f of n strictly larger than that of g of n?
It's also.
Turns out it's true. And I'll show you how to reason about that later. But n log n has a higher rate of growth than n, a little bit higher. Okay? Would it be also accurate to say big O? Yeah. Which gives you more information? Saying that g of n is big O of f of n, or saying that g of n is little o of f of n? Little o. Because if you say, when you say little o, it rules out the case where g of n and f of n are the same, exactly the same. In this case, we have it written here, it's true, but you couldn't tell without looking over here that in fact f of n grows slightly faster than g of n. Little o would give you that. Right? Okay, so here are some examples, and I just blew right past them last time. But there we've got 3n squared plus 5n plus 3, and we're trying to characterize it. It's O of n cubed, right? With big O, you can be as sloppy as you want. Typically, you try to be as tight as you can be. What's the tightest you could be with big O notation to give a constraint on that thing? O of n squared. And you see there, it's O of n cubed, it's O of n squared log n, it's O of n squared. It would be inaccurate to say that it's O of n log n, or O of n or O of 1, because those are smaller rates of growth than n squared has. And you can see it's bounded from below by 1 and n log n and n squared. So it's theta of all those things. It's not theta of n squared log n, and it's not theta of n cubed. Theta, omega, I should be saying. So look at that and see if there are any that have any questions about why it's not true, or why it's true. Yeah.
So maybe this is a little off topic, but can you find little o's and thetas that are in between? So like, can you find something between n log n and any other one? Like, can you always get more fine? So like if you had like
yeah, okay, so let's say you're talking about you have n and then n log n and then n squared. There's something in between.
yeah, like will there always be something in between?
Yeah, well, if we, you know, there are lots of functions in the world, but The ones that occur most often in algorithm analysis are going to be polynomials like n squared, n cubed, and then logarithms, log of n. But you'll also see log of n squared, log of n cubed. And so, yeah, you could go n and then n log n, and then n log n log n, and n log n log n log n, and so on, and then n cubed. So yeah, you can always find things in between. Any other questions? Okay, and I made a point about this. I'm just going to repeat. Sometimes, most often, we use complexity notation to make statements about specific algorithms. So when we say that selection sort, for example, is O of n squared, what we're saying is that no case will take longer than n squared time. Okay? Or another way to say that is the worst case will take no longer than n squared time. Or if you find the worst case of selection sort and figure out its complexity, its doubling behavior will be that when you double the length of the worst case, the running time quadruples. All ways of saying the same thing. When you say omega of n squared for selection sort, you're giving a lower bound on the best case. So you're saying in the best case, it never goes faster than n squared, even in the best case. And since those two match, you could just say selection sort is theta of n squared. It'll always take quadratic time, no matter how the elements are initially arranged. What happens when I... Okay? So you're used to that. And I just want to disabuse you of the notion that big O means worst case. It's often used to characterize the worst case, but it just means upper bound. And same thing goes with omega. It does not mean best case. It means lower bound. So it's perfectly fine to say the best case of selection sort is O of n squared. You're just putting an upper bound on the running time of the best case. You can put a lower bound on the running time of the worst case. So this is insertion sort. We already looked at the animation of it, and we know that there's somewhere between about n and about n squared data comparisons. That's the difference between the best case and the worst case. So if you count through it carefully, if it's already sorted, they're just going to be n minus 1 comparisons and no swaps. And that's when it's already sorted. If it's already in the opposite order of sorting, then it's going to be 1 plus 2 plus 3 up to plus n minus 1 comparisons using analysis like we did at the beginning of the lecture. And that sums to something that's a quadratic. So, because the worst case and the best case don't match, we can't say it's theta of anything. You can't say insertion sort's theta of n squared, because sometimes it's faster than that. You can't say it's theta of n, because sometimes it's slower than that. So the best you can do is say it's O of n squared, and it's omega n, and then you can just add, and by the way, those bounds are tight. They can't be improved. Sometimes people will invent algorithms, and they have a hard time analyzing the worst case. And so they say, I'm not sure exactly how tight this bound can be, but it's no worse than O of n to the fifth, let's say. And then it may take time and other researchers to figure out, okay, this bound isn't very good, we can improve it. So that's the flexibility in big O allows for that. But insertion sort, we're sure, is O of n squared, omega of n, and the bounds are tight. Okay, and this slide always causes problems. And I talked about it last time as well. Sometimes we're not trying to put bounds on individual problems, on individual algorithms. We're making a statement about some problem. So think about the problem of sorting numbers into order. And there are lots of algorithms that have been discovered, and there are an infinite number that have not been discovered or named or whatever. So when we say sorting is omega of n, we're making a statement about every algorithm there is, whether it's been discovered and named or not. And when I say that it's O of n log n. Again, I'm making a statement about every algorithm there is out there, whether it's known or not. So I'm sort of making a statement about nature. You know, it's the same thing if you say the speed of light is c. That's just a constraint of nature, and you can think of the fact that you can't do comparison-based sorting in better time than n log n in the worst case. That's also a statement about nature. So when I say that the sorting problem is omega of n, what I'm saying is that the worst case of every sorting algorithm is omega of n. For any sorting algorithm out there, every one of them is going to have a worst case that's omega of n. It's easy to see why, we said last time. Because every algorithm has to at least look at every element. Right? And so that's what omega means when it's applied to problems as opposed to individual algorithms. Big O, when it's applied to algorithms, you're making a statement again about every algorithm, but you're saying that. So when I say that comparison-based sorting is O of n log n, I'm saying that, this case, I'm saying among all of the algorithms, there exists one that's O of n log n. So the omega statement is saying for all. The big O is saying there exists. Yeah?
Just double checking, because I was under the impression that best case for all sorting algorithms was n, and it can get worse than that. So how does that, am I misunderstanding the top sentence
No.
there? Or?
No. But what it means is when you say that a problem is omega, if you give an omega bound on a problem class, you're talking about, you're giving a constraint on the worst case for every algorithm. Okay? And look at the second one. Comparison-based sorting. So the difference is comparison-based sorting is sorting when all you're able to do for elements is compare them and swap them. You're not able to take them apart and look at their bits. So it has been proven that comparison-based sorting is omega of n log n. So that says that every comparison-based sorting algorithm, the worst case is omega of n log n. But we know that there are algorithms that have best cases better than that, right? Insertion sort, for example, has a linear time best case. It's a comparison-based sorting algorithm. But that statement right here is about the worst cases of all algorithms out there. Now, if you had to, what's the proof that shows that comparison-based sorting is O of n log n? What's it take to prove that comparison-based sorting algorithm has that upper bound? Yeah?
Is that there is a comparison-based algorithm that is O of n log n?
Right. Merge sort. Right? To put this upper bound, you just find, you say, okay, here's this new algorithm called merge sort, and its worst case is n log n. Ergo, comparison-based sorting is O of n log n. Now, what if you wanted to lower that bound? What if you want to become famous and show that actually it's O of n? What would you have to do?
Discover a comparison-based sorting algorithm that's O of
Right.
n.
You just have to discover a better algorithm. That's O of n. Now, so it's easy to see how you can put a big O bound on a problem class. You just find a better algorithm. What about the lower bound, the omega?
That's not moving.
Well, what about this first one here? Sorting in general is omega of n. Meaning that every algorithm every algorithm out there is going to have a worst case that takes linear time.
You have to check every element in the list at least, right?
Well, you can't look at every sorting algorithm. Right? So it can't be the case that you just look at every sorting algorithm in the book and make sure that its worst case is linear, because lots of algorithms aren't in the book. So you just do it just involves a different kind of proof. You don't prove the lower bound by looking at individual algorithms. You have to think about our algorithms in some way. You make the argument that I made before, that they've got to at least look at every element. That'll take linear time. Later in the semester, we'll see how to prove that omega of n log n bound for comparison-based sorting. But what that says is that merge sort runs in time n log n, and you can't do better. asymptotically speaking. Oops. Okay, there we go. Nope, that's not where I want to be. Just bear with me. Okay. Okay, I'm going to define, we're going to use little o here. I'm going to define something called domination, when one function dominates another. And I'm just going to say if f of n is little o of g of n, I'm going to say that g of n dominates f of n. It just means grows faster than. So if the rate of growth of g is bigger than the rate of growth of f, we say that g dominates f. And we can compare common functions in order of domination. So this is another good thing is just to commit to memory. A factorial, n factorial dominates any exponential. And we're only concerned with where the base of the exponential is greater than 1. So n factorial dominates a to the n for a greater than 1. A to the n dominates n to the a. So exponentials dominate polynomials. And here we want a to be greater than 0. Any polynomial dominates any power of a logarithm. So what about the if you look at trying to compare n to log n to the 100th power, which grows faster? N. What about n to the 1/1,000,000th power and log of n to the 1,000,000th power? Which grows faster? N. The n to the raised to the 1/1,000,000th. So any power of n, no matter how small that power is, grows faster than any power of a logarithm, no matter how big the exponent is. Okay? Polynomials grow faster than logarithms, and logarithms go faster than constants. Okay? And then within one of these classes, you see the note over there, exponential. So 2 to the n, or 3 to the n grows faster than 2 to the n. For polynomials, n to the 5th grows faster than n to the 4th. And same thing for logarithms. Log of n squared grows faster than log of n. So that domination information is good to remember. Now, a rule of thumb, when let's say you do an exact analysis and you end up with a complicated term, expression, you want to simplify it. You don't want to say it's O of 3n squared plus 5n minus 2. You want to simplify it. So what you do is, what you just need to remember is that you can ignore leading constants. So if you're trying to figure out is 10n squared O of n squared, the answer is yes, because you can ignore leading constants. You can ignore low order terms, and that's where the domination comes from. So if you have g of n plus f of n, and g of n dominates f of n, you can just throw the f of n away. And just say it's O of g of n. And then we've got this product thing here, which looks complicated and isn't, but I'm going to let you look at it, and I'm going to do some examples later that will make more sense. But if you've got the product, what this is supposed to do is take care of cases where you're multiplying, let's say, n log n. How does n log n compare to n squared? Because you can't, there is no entry in this table for n log n. We can deal with comparing n squared and n cubed and comparing n and log n, but multiplying n log n, what do? That's what that third rule does. It says you break f into 2 pieces and break g into 2 pieces and compare them. I'll explain that in a second. So that's just saying what I've been saying. All right, so let's do some simplification examples using those rules. How do you argue that 3n squared plus 5n minus 3 is the same as n squared in terms of order of growth? Yeah?
Because the largest order term is n squared?
Yeah. He said the largest order term is n squared. You get rid of the low order terms, the ones that are dominated by the high order term. So n squared dominates all the others. So you get rid of that. You get rid of the leading constant. And all you got left with is the n squared. So drop the low order terms, drop the leading constant. What about this one? How do we show that 15 is dominated by log n? Yeah.
Because all constants are dominated by all logarithms.
Yeah, you hark back to the table I showed you, and constants are dominated by logs. Okay? What about that one? How do you argue that log n is dominated by log n squared? Yep.
Looking back at the table, for logs, the higher exponent dominates the lower exponent.
Yeah. The table says this as well. Powers of logs, higher powers of logs dominate lower ones. What about that? The 30th power of log n, how do you show it? What's the argument that it's dominated by n? Okay?
Polynomial dominates
Yeah.
logarithmic.
Powers of powers of n dominate powers of a log of n. About that? Yeah?
I just have a question. So, so like all logs will dominate all constants as they approach infinity? That's
Yeah.
what we're implying.
Yeah. So the rate of growth, we're interested in what happens to the rate of growth as n gets large. Yeah. The constant may start out way bigger than the log, but eventually the log will catch up and pass it because it grows faster. Okay? This is just another consult the table deal. Higher powers of n dominate lower powers of n. So we're just going through the table here. Where I want to show n to the fifth is dominated by 2 to the n. That's just in the table as well. Exponentials dominate polynomials. Okay? Higher exponentials dominate lower ones. 5 to the n dominates 3 to the n. Factorial dominates exponentials. Okay? Great. Now we got one of these mixed examples. What was that third rule that I sort of went over, didn't go over very well? I want to show that n log n is dominated by n squared. So this is how you do it. You want to split both sides into two pieces. So what I've done is I split the n log n. I've got the n here. I've got the log n here. So this is n log n if you look at it. And I split the n squared into n and n. And then you've got to show that one of the pieces on the left-hand side is big O of one of the pieces on the right-hand side. And you've got to show that the other piece on the left-hand side is little o of the other piece on the right-hand side. So we've shown that this n is big O of one of these n's, and this log n is little o of the other n. So basically, we're sort of factoring the two sides. We're factoring out the things that grow at the same rate, and what's left had better dominate. What's left on the right-hand side needs to dominate what's on the right-hand side. So we know n is big O of n. We know log n is dominated by n. Put it together by the multiplication rule, and you get that. Okay? So split it into two pieces on both sides, and set up, show that you got a big O relationship here, a little o relationship there, and then you can conclude that the product, the right-hand side product dominates the left-hand side product. Let's try it again. How would you show that n is dominated by n log n? What would be how would you split up the two sides? Okay?
1 and n.
Okay. So we could split the n into 1 and n. And what could we split the right-hand side into? N and log n. And then we have that n is O of n. That's the parts that are the same rate of growth. And what's left is the 1 is little o of log n because of the domination table. Multiply them together, you got n times 1 is little o of n times log n. So, not hard. Another one. 100 times 2 to the n is dominated by n times 2 to the n. So what's the piece from both sides that grow at the same rate? 2 to the n shows up on both sides, so we say 2 to the n is big O of 2 to the n. Good. And what's left is the 100 and the n. The 100 is dominated by n, therefore the product relates that way. It just about works. You can just think of it as, okay, we'll just divide out the 2 to the n's and look at what's left. That's sort of how it works. Okay? All right, so what we've done is I'm trying to build up your intuition about this notation because we're going to use it so much. And everything that I've said is the way we'll reason about big O notation and theta notation and so on in class, sort of informally. But lurking behind is something I haven't talked about yet, is the actual formal definition of big O that all these rules of thumb come from. So let's take a break and we will see what's the justification of everything I've been saying. Okay. Now, let's talk about the actual mathematical definition of big O. And this is the version the book gives. Let f and g be functions from positive integers to positive reals. And we say that f of n is big O of g of n if there is a constant c greater than 0 such that f of n is less than c times g of n. So that's what the definition the book uses. It doesn't do much with the definition. And my experience, and it's not the standard definition that you see in other books. I've gone back and forth over the years, but I think it makes it easier to work with if we use the definition used by most every other book. So this is the definition we're going to use, traditional definition. It amounts to the same thing. When you're trying to do proofs using the first definition, it's a little bit harder, in my opinion, to do than if you use the second definition. So here we say let f of n and g of n be functions from reals to reals. So already we've got to change. The traditional definition says that f of n, f takes a real as input and returns a real as output. This is from positive integers to positive reals. And this says we say f of n is O of g of n if there are two constants such that that inequality holds. And so this definition looks more complicated and is more complicated. But when you're doing proofs with it, you're just doing proofs using real numbers, whereas in the previous one you have to make arguments about involving integers as opposed to just inequalities. So we're going to try to understand that definition and see how to make use of it to show, to justify some of the things we've been doing. So we'll come back to that. So like they're equivalent, but I'm going to go with this. So here's an example. F of n is 1 over n plus 2. So that's the blue curve. And then the pink curve is just g of n equals 1. So according to that definition back there, is f of n O of g of n. Remember, f is the blue curve. I'll start with a different one. Is g O of f?
Yes.
Okay? So remember, we're talking about rates of growth. And but you can be sure that if you graph one function and you graph the other function, and the one function is always above the other function, as in this case, then yeah, the pink is O of the blue. And in fact, what are their rates of growth? What's the doubling behavior? If you double n, what happens to the pink? Stays the same. If you double blue, okay. Well, and let's look. We're only interested in the long run. We don't care what happens near 0. We just want to know as we head towards infinity, what happens what happens to doubling behavior. Essentially, it's constant. I mean, you could say technically, if you double it, it goes down a little bit. But after a while, in the limit, the thing is flat. So, in any event, no one argues with me that the pink is O of the blue. But also, the blue is O of the pink. And I do get arguments about that. Okay? What's the justification? Yeah?
So if you just chose the constant 3, then some of the pink is above the blue for the vast majority.
Okay. So the formal definition, the reason they're both O of the other is because they have the same growth rate. They both tend toward being constants. But to use the formal definition, what that definition says is, okay, if you want to argue that the blue thing is O of the pink, in other words, that the rate of growth of pink bounds the rate of growth of blue from above, what you do, you get to multiply pink by any constant you choose. So let's choose 4. The game we're trying to play is multiply this pink by a constant so that it gets above the blue everywhere. Okay? So what happens if we multiply the pink by 4? Where would the line be? Right at 4. Is it over the blue everywhere?
Not everywhere.
Not everywhere. Not over here. Okay? But there's another thing in the definition. the definition of everywhere, we get to pick another constant, and we say, let's say we pick the other constant 2. We're saying, okay, after we multiply by the one constant, we're allowed to ignore everything smaller than 2. And then I want what's left of the pink to be bigger than what's left of the blue. Is that the case?
Yes.
So if I scale pink by multiplying it by 4, and I get it up here, and then I say, and ignore everything to the left of 2, is the new pink line going to be above the blue pink line everywhere? Yes. Therefore, the blue line is O of the pink line. That's what a formal proof looks like. You just got to show these two constants exist. That you can multiply, you can scale one of the curves with a constant, and then ignore everything to the left of some other constant. And you've moved the one curve above the other everywhere. Okay, so back to the definition here. You see, we have to find two constants. C, that's the 4, the scaling that I did. So think of C as the scale, and N0 is the cutoff. And so we're trying to show that when you multiply G of N by C, that F of N will be less than C times G of N for all N greater than or equal to N0. That's the formal definition of big O. From that, all those rules of thumbs come, like you can ignore leading constants, or you can ignore low order terms. Let's look at another one. Well, I guess we'll look. Okay, I'm not going to dwell on this at all because we're going to do nothing about it. I just want to show you. This is the definition I just gave you. And if you're curious, these are the formal definitions of the other 4 classes. They look kind of the same, but the only one we're going to work with is this big O one. So I'm just going to fly right past it. So it's emphasized right there. Okay, so let's see what we got here. I want to show that 5n squared is O of n squared. Or you can also think of this as sort of a justification of why you can ignore leading constants. 5n squared is O of n squared. We want to find a way to scale that green curve so that it is at or above the red curve, at least when we're to the right of some cutoff that we get to pick. Okay? So there are various ways to approach this. One way is just to do it by inspection, figure out the constants for yourself, and then show that it works. So just looking at that, what can we multiply the green curve by so that it's at least as big as the red curve everywhere? 5. So we could just say, okay, a constant of 5 will work. And then what about a cutoff? Yeah, they'll be the same curve, so we could pick any N0 that we want. And up there, I just solved for it. So let's see what I did. I wanted 0 to be less than or equal to 5n squared, less than or equal to c times n squared, for all n greater than some N0. Okay? And then I basically divided through by n squared. And to do that, I have to make sure n squared is not 0. And so I assume that N0 has to be positive for this to work. So divide through, and that simplifies to 0, less than or equal to 5, less than or equal to c. Okay? So that just says that for this proof to work, c has to be 5 or bigger, and naught has to be positive. Actually, n0 of 0 would work as well. So you can either work by your own intuition and figure out some constants that work, or you can you can just manipulate the inequalities and derive. Now you'll notice there's one constraint I haven't said much about. That's technically you have to show that that f for 5n squared to be O of n squared, it needs to also, the 5n squared needs to be positive. It can't be negative. But that's almost never a consideration when we use complexity analysis in this class. Why would that be? What would it mean if we had negative, if functions could be negative like that?
You'd have less than 0 comparisons.
Right, you'd have -5 comparisons. Your running time would be -7. You just don't see things like that when you're doing time analysis. But these proofs, we'll try to be faithful and show that the function's positive, but it's just never not going to be the case. Okay? Now, I also get students worry because there's not a unique answer. C equals 5, n naught equals 1 is an answer. C equals 1,000 and n naught equals 1/2 is an answer. In this case, any C greater than or equal to 5 will work, and any n naught will work as long as it's not negative. So that's just the way it is. How do you prove that 5n is O of n squared? So I've graphed them, and you'll see that 5n, the red curve, is bigger for a while than n squared, which is the green curve. But eventually n squared takes off. It gets bigger because n squared grows faster than n. So it's obvious from the graph that 5n is O of n squared. But to do the proof, we have to find a constant c and a cutoff n naught. So what would work? Yeah.
For this case, would it be alright to prove that 5n was big O n, and then deduce that then it's also big O n squared?
Okay, so he's saying, would it be, we could say could we show 5n is big O of n, and n is big O of n squared? And that's how you do it using the rules of thumb. Basically you say, okay, just throw a leading constant. But here I'm asking you to justify, when I say do a formal proof, I want you to do your reasoning directly from the definition of big O as opposed to using the rules of thumb that follow from it. So up there I go through the derivation and I come up with let C be 1 and n naught be 5. Forget that. How would you have gotten the same answer just by looking at the graph? What's special about 5? That's where they cross. So if you just say, okay, look to the right of look to the right of here. So let n naught be 5. And everything to the right, the green is already bigger than the red, and so we just let C be 1. Now, suppose I were contrary and I said, okay, I want n naught to be 1. I want you to do a proof that 5n is big O of n squared, but I want you to use n naught to be 1 for whatever reason. What C would work then? So if we're going to have our cutoff be right here, I have to wait for that thing to go away. Anyway. If we let our n naught cutoff be right here, what we have to multiply the green curve by so that it's above the red everywhere to the right of 1?
10? 5.
Well, let's see. So at 1, this red will be 5, and this will be 1. 1 squared is 1. 5 times 1 is 5. So multiply it by 5, that'll bring the green curve up, and then it will take off. So you could use n naught equals 1, c equals 5 if you wanted to. Or you could just say, okay, let n naught be 1 billion. Lots of ways to do it. That's one way. I mean, if you like having a way to plug and chug, that's what I've done up there. The usual thing I do is accept inequality, I divide through by the higher order term, and that gives me a constraint on C, and usually along the way to doing that, you discover n has to be bigger than something to make the proof work. Okay? Okay, here's one. The green curve is log base 2 of n, and the red curve is log base 4 of n. So let's think about n naught first. How big does n naught have to be?
At least 1.
Okay, said at least 1. Why does n naught have to be at least 1? Because it goes negative over here. So we've got part of our obligation is to show that we can pick an n naught such that our functions are always positive. So we need to make n naught at least 1. Okay, what do we multiply by?
Log base
Turns out you multiply by log base 204. The important thing is to realize that these two curves differ by a constant. The base of the logarithm doesn't matter in big O notation because it's just a matter of multiplication. It's a leading constant. So if you multiply the red curve by 2, you've got the blue curve. So we can let n naught be 1 and c be 2 and get this. I picked a different n naught for whatever reason, but you get the idea. Right? Here's one. N squared plus 5n is O of n squared. So we got the green curve, which is below the red curve everywhere. But nevertheless, we got to show that its rate of growth bounds the green curve bounds the red curve. So, you know, you can go through the way I did it there. So I've been skipping my derivations up here. We've got this inequality we have to show. If n, as long as we make n naught be positive, we can divide through by n squared, and we get 0 less than or equal to 1 plus 5 over n less than or equal to c. Okay, so far so good. And then if we make, why is this assumption that n not greater than or equal to 5 made?
Because then we can say that 1 plus 5 over n is less than or equal to some constant thing.
Okay. So it looks like what I did here is I just picked a 2 I just arbitrarily picked a 2 because I had to pick some constant for c, because you can make n naught and c be various things. So I picked 2, and as long as n naught is greater than or equal to 5, this inequality will be true. So those, so 2 and n naught equals 5 work. If I'd written a 10 here, I would have come up with a different n naught. So this is sort of overkill up here. Really, it's just a matter of picking an n naught and then seeing how much you have to multiply the green curve by to make it cross the red curve and stay above it. That's what these proofs amount to, just finding the n naught and the c. So that is actually animated there. So for c equal 2 and n naught equals 5, I'm multiplying the green curve by 2, and you get that. It crosses at 5. So you can pick where you want the crossing point to happen and then multiply by, figure out what constant you have to multiply by, and that's what you get. All right, let me ask you some other questions. What about this? Let's let f of n equal 1, and let's let g of n equal 10 plus cosine of n. Okay? Is this true? So if I ask you to come up, basically, if I'm doing a proof, I'm asking you to find a c and an n naught that would, when we plug it into the definition, would work. What would you say? Let's draw a graph here. What would f look like? F's going to be a straight line at 1, and let's put 10 up here. What would g look like? So it's going to look like, what's cosine of 0? Is that 1? So it would look like something like that. Okay? It's obvious that f of n is O of g of n because 1 is always below that curve. So you can pick any n naught, any c that you, well, you can say n naught equals 0, c equals 1. And we're good. Now, what if we want to show the opposite? What if we want to show that g of n is O of f of n? big O of f of n.
Yeah, so C equal to 12.
Right, so we say, so this thing tops out at 12 up here, right? It goes between 12 and, not 12, 11. 11 and 9, the way I've got it scaled. So if we just let C equal 11 would work. That's the smallest we can make it. N naught equals 0. That's going to make this curve be right up here. I didn't quite draw it right. It'll be touching. And then we're good. That's what these formal proofs look like. So, just want to ask you two more things, and then we'll be done. So, when you're doing a proof of the form, you want to show that f of n plus, well, let me make this more concrete. Suppose you want to show that n squared plus n is O of n squared. Okay? No, that's not what I want to do. Let me try a different thing. Let's do this graphically. Suppose you have a function that's really big at first and then does something like that. And you've got another function that stays down and then starts to climb faster. How do you deal with that? When you're choosing n naught and c, what's the trick for dealing with a function that starts out bigger but grows slower?
Pick your n naught such that you ignore the
Right,
starting
you
out.
just pick an n naught where they cross. So if that's where they cross, you just pick an n naught where they cross in a c of 1, and that's good. Okay? So you can forgive all kinds of bad behavior just by saying, okay, ignore all the bad behavior to the left. And then similarly, what if you've got a function like n and you're trying to show that, and a function like 5n, and you want to say 5n is O of n? How do you get around the fact that n is always lower than 5n, but we need to somehow show that it bounds 5n? That's where you pick the constant. You pick a constant to make it big enough, and then n naught doesn't matter. So that's sort of two extremes. Okay? Let's stop there.